Today we're going to be looking at double integrals in polar coordinates. So that again means finding areas and volumes. We did one problem, I think a couple days ago, where we had to look at a region and we ended up having to use trig substitution in order to solve the problem. And that problem could be done much easier had we used polar coordinates. So let me remind you a little bit about a polar rectangle. Okay, so what's a polar rectangle? Well, we all know what a regular rectangle looks like. Okay, so polar rectangle looks something like this. Okay, so that's the rectangle. So this is the angle theta is this. So we're going to take from here I'm going to call that beta. I'm going to call that alpha. Okay, this distance is going to be r. That's our radius. Okay, and then we can have a r1 here. And that's equal to A, and maybe an R2 here. Let's call that B. Okay, so as we can see, we're going to have the fact that 0 is going to be less than A and less than B. Okay, we want to make sure we actually have something. Okay, so if we have the whole thing, we would have an angular ring. So we just have that only little bit. So now we want to talk about the area of the circular sector. With radius r. All right, so I want to have a central angle. So a central angle might be going through here. We can call that theta. And that's the central angle. And so theta is 1/2 no, skip that. That doesn't make any sense. Okay. All right, so the area of the polar rectangle okay, is going to be the area of the big piece minus the area of the little piece. So the area, so if you, okay, now I know what I was writing. So if I have a theta is a central angle, that would imply that the area would equal 1/2 r squared times theta. So the area of the polar rectangle. So we're going to take the area of the big piece. So the area of the big piece is going to be 1/2. The radius is b squared because we're already out. I didn't mean to write b2. I just meant to write B. So we go all the way out here. So we're going to go from here all the way out to B. And then the angle is beta minus alpha. Then we're going to do the area of the smaller region. So this time I'm only going to go out to here. So I'm going to have A squared, and I'm going to get beta minus alpha. So this is going to be 1/2. I'm going to get B squared minus A squared times beta minus alpha. So that turns out to be 1/2 B minus A, or B plus A, times B minus A times beta minus alpha. And so B plus A over 2, if I just take this B plus A over 2 part, that's the average value, the average of the of R. So that looks like R bar. And then this right here, B minus A, that's just the change in R. And then beta minus alpha, that's just dr. So the area of that little polar region is R dr d theta. Okay, so that's the area of that one little polar region. All right, and we're talking about this area right there. Okay, so now what I want to do is I want to do the same thing. Y'all know y'all used to me doing Riemann sums and all that kind of stuff. So now I'm going to take another pretty much polar area. And this time I'm going to divide it up into a number of cells. So we're going to make a partition of this. And so now I have a polar partition. And with this polar partition, I'm going to divide my region A to B. So A is going to equal some R0, which is going to be less than R1, which is less than R2, which is going to go all the way up to Rn, which is going to be B. Okay, so we'll actually that's this partition right here of the radius. And then alpha is going to start with some theta naught less than theta 1, less than theta 2, less than all the way up to some theta n, which equals B. So now we are partitioning that this way. Okay. So this one little piece right here might be a delta theta, and that one little piece might be a delta R. Okay, so now we're going to take a selection. So that means On every polar rectangle, I'm going to choose 1 point. Okay. So that means on each one, I'm going to choose a point inside each cell. That's my selection point. And now I can evaluate the function floating over top. So now I get that my area is approximately the sum, I equal 1 to n of f of x I star, y I star, because we're still choosing the x and y coordinate points, delta I. And I think normally I use k, so let me stick with my normal notation so as not to confuse anybody. Okay. So I'm going to rewrite that as the sum k equals 1 to n f. So now what is xk star? Well, that's going to be rk star cosine of theta k star. And then y is going to be rk star sine of theta k star. And dA is going to be Ri star delta R delta theta.
Should it be RK?
Yes, thank you. Well, at least I know y'all listening. Okay. So therefore, I get now that the area is going to be the limit as n goes to infinity of the sum k equals 1 to n of this f of rk star cosine of theta k star, rk star sine of theta k star, rk star delta r, that doesn't look like a delta, okay. And we all know what happens to this. Now we have two things. We have delta r and delta theta, so that lets me know I have a double integral. So I have a double integral, okay? So r goes from a to b, and theta goes from alpha to beta. This becomes f of r cosine theta, r sine theta, r dr d theta. So before, where we had dx dy, whoops, that's not right. We now have r dr d theta. Okay, and that's how we're going to do all of ours. Okay, so just to make sure you know that this matches our old notation, this is just a double integral over R of f of xy dA in polar coordinates. Any questions? Okay. Let's do an example. Okay, so find the double integral over the region of x plus y dA, where R is the region in the first quadrant bounded by the lines y equals 0, y equals the square root of x, the square root of 3 times x, and the circle R is equal to 2. Okay, now we can clearly see that if we were to look at this problem in Cartesian coordinates, what will we have? So in Cartesian coordinates, I would have this. This is fine. This is, I can see that this is clearly horizontally simple. Okay, so for this curve right here, I could write it as x is equal to y over the square root of 3. But for this curve, I would have x is equal to the square root of, and that should be 4 because it's a circle of radius 2. So that should be a 4. And that's not a whole lot of fun. I would get the area. Oh, I still have to figure out where these two meet. So where yes, I need to then solve y over the square root of 3 has to equal the square root of 4 minus x squared to find this value of y. And then I would get my area would be the integral I would have to say x would go from y divided by the square root of 3 to the square root of 4 minus y squared. And then y would go to 0 to whatever that y star is that I find. And then I would have x plus y. And then I would have dx, dy. And of course, when I'm finished this, I'm going to have to use trig sub again. Actually, maybe not. Actually, that's not, it's not, this one's not too bad. I can actually do that one without having to use trig sub. But instead, let's do it the way we want to do it, which is using polar coordinates. Okay. So again, now we want to look at this. So we want to look at this in terms of r and theta. And so this line okay, so this line right here, y is equal to the square root of 3x. Well, if I switch over, I now get, that means y is r sine theta is equal to the square root of 3 times r cosine theta. So that means the tangent of theta is the square root of 3. So theta is pi over 3. So I can also write this line as theta is pi over 3 as such. And I also know that my radius of this circle is 2. So now this is a fairly easy integral. I get that the integral over the region of x plus y dA, well, I can see that r goes from 0 to 2 and theta goes from 0 to pi over 3. X becomes r cosine theta plus r sine theta. And now I have r dr d theta. So the r's in there factor out. So I end up with the integral from 0 to pi over 3. This is actually completely an integrated integral. So I can actually move the thetas and the r's if I want to separate integrals. So one of the things I can do for this problem, this becomes r squared times the cosine of theta plus the sine of theta dr d theta. Did I forget my integral? So now notice that theta and r are completely separate. This is one thing I have not done, but you can do with iterated integrals. If they don't have anything to do with each other, I can factor all the theta out. So I can actually write this as the integral from 0 to pi over 2. I don't always do this, but I can. Of cosine of theta plus sine of theta d theta times the integral from 0 to 2, and this is supposed to be pi over 3. Pi over 3, pi over 3 of r squared dr. So you can do that when they separate completely. Sometimes you can actually compute the integrals separately as well. So these separate. They don't always do that, but they do. Okay? This integral is easy. It becomes 1/3 r cubed, evaluated from 2 to 0 to 2. So this just becomes 8/3. So now I get 8/3. And then when I do the other integral, cosine integrates to sine of theta. Sine integrates to minus cosine. And it's evaluated between 0 and pi over 3. So I just get pi over 3, I'm sorry, 8/3. And then I get the root of 3 over 2 minus a half plus 1. So my answer is 4/3 the root of 3 plus 1.
So you can just do like separate them and
When they, only in certain cases do they separate. So if the functions are attached, you can't pull them apart. But if they separate like that, yes, you can separate them. Not all of, and even with the X problems, because I'm on a, see, the reason why I can do that is because all of these are constants. They're not functions. You can only split it like that. Remember when they're functions, you can't split it.
Okay.
Okay. So calculate by double integration the area of the region bounded by x squared plus y squared is 4. Now this is an easy problem, okay? Because the region x squared plus y squared is 4. That's just a circle. Okay. All right, so clearly you can see that in order to evaluate this area, this is my region. This whole thing is my region. And theta, well, r goes between 0 and 2. Okay. And then theta goes all the way around the whole circle. So theta So again, my limits are constants. All right, so if I'm calculating area, that means I'm calculating the double integral over the region dA. That's it. So this is the double integral. R goes from 0 to 2. Theta goes from 0 to 2 pi of R dr d theta. And this is another one I can split up if I want. This is the integral from 0 to 2 pi of d theta, the integral from 0 to 2 of R dr. So this first integral, just 2 pi. And this second integral just becomes 4. No, becomes 2. So therefore my answer is 4 pi, which is what we're supposed to get, right? Pi r squared. Okay. Here's another one. And this is another one that we're not worrying about whether or not we have a function. So find the volume of the region bounded above by the plane Z is equal to 4 plus X plus 2Y, and on the sides by the cylinder X squared plus Y squared is equal to 1, and below by the XY plane. Okay, so here's another easy one. If it's a cylinder, that means in the XY plane, the region R is just a circle, X squared plus Y squared is 1. And so I can take my region and I can say theta goes all the way around the 2 pi, and R goes from 0 to 1. So therefore the volume is a double integral over the region Z of X and Y dA. But I'm going to switch that to polar coordinates. So theta is going to go from 0 to 2 pi. R is going to go from 0 to 1. Z now becomes 4. X is R cosine theta. And Y is R sine theta. And then I'm going to multiply this by r, dr d theta. Now here's one I can't separate, okay?
That makes sense.
And the reason why I can't separate it, because I can't pull the r or anything all the way out. So this is the integral between 0 and 2 pi. The integral between 0 and 1. I'm going to get 4r plus r squared cosine of 2 theta. Oh, sorry, no, cosine theta. Plus 2r squared sine of theta dr d theta. So we're going to integrate with respect to r first. This is going to give me 2r plus 1/3 r cubed cosine theta plus 2/3 r cubed sine theta, evaluated from 0 to 1 d theta. So I get the integral from 0 to 2 pi.
Dr. Lott,
Yes.
shouldn't it be 2r squared or r squared?
What did I?
Okay, I'm not sure.
No.
4r integrated.
Oh, this is 2r squared. Yes, that's correct.
Thank you.
Yeah. I thought you were talking about the other ones, the cubes, but that is correct. I agree with you. Okay, so now I'm just going to get 2 plus 1/3 cosine theta plus 2/3 sine theta d theta. So now I'm going to get 2 theta plus 1/3 sine of theta minus 2/3 cosine theta, evaluated between 0 and 2 pi. So now I'm going to get 4 pi minus 2/3. Then I'm going to subtract off negative 2/3. So again, I get 4 pi. Okay. Okay, so find the volume of the solid region inside the sphere x squared plus y squared plus z squared equals 4, and outside the cylinder x squared plus y squared equals 1. And above the xy plane. Okay, so this is like a cored apple. All right, so we have a sphere. And then somebody comes along and says, I want to look at this cylinder. Okay, so what they're asking for is the volume of the region inside the sphere and outside the cylinder. So they want the core, what's left after you core an apple. Everybody see that?
Yeah.
Okay, now they only want the region above the XY plane. If they wanted the whole thing of the cored apple, we could just find the region above the XY plane and we could double it. Okay? All right, so now if we look at this, what does this look like in the XY plane? What's our region R? So we need to find okay. So it's not too difficult. All right. In the XY plane, hey, I did that pretty well. Quite proud of myself. It's not going to be drawing to scale, but it looks pretty good. So in the XY plane, that says Z is 0. So the level curve of x squared plus y squared plus z squared is equal to 4. That level curve just comes down here as x squared plus y squared is 2. And we already know we have the cylinder in the xy plane, and that comes down here as x squared plus y squared is 1. Okay, so so our domain or our region is this stuff in between. All righty. So now it's clear to see that theta goes all the way around, and our radius r starts here and goes to there. So therefore r starts at 1 and it goes to 2. Now our surface over top z that's enclosing our volume or our solid is z is going to be the square root of 4 minus x squared minus y squared. So I can very nicely make that z is the square root of 4 minus r squared. And this becomes such a nice integral. So therefore the volume turns out to be theta goes from 0 to 2 pi, r goes from 1 to 2. Our function z on top becomes the square root of 4 minus r squared. And then r d theta makes this a nice, easy integral because of the r. Okay, so use substitution, you just get the integral from 0 to 2 pi. I'm going to have 1/2, I get the 2/3 times 4 minus r squared to the 3/2 from the integration. And that's evaluated from 1 to 2 d theta. So that becomes the integral from 0 to 2 pi of 1/3 Do I really have 1/3 3 to the 1/2? I sure do. I have 1/3 3 to the 1/2, but 1/3 3 to the 1/2, that doesn't make sense. 1/3 3 to the 1, 3 to the 3/2. It's just the square root of 3. D theta. So that becomes 2 the root of 3 pi. All right, all those were fairly easy. And the reason why they were fairly easy is because all the limits of integration were constant. So now let's look at regions that are not, that we have to look at that may be simple, okay? Okay, so what is a radially simple region? Okay, it's radially simple Okay, so this region is radially simple if maybe it looks as such. Okay, so the region I'm looking at is the region in between. So I can see now that I'm going to call this R is H1 of theta. And this one up here is R is H2 of theta. So notice the radius changes depending upon what the angle is. Okay. So here, on this line, theta is equal to on this line, theta is theta 1. And on, well, I'll just call it alpha, like we've been calling it. And over here, theta is beta. And again, I want to find that's my region. All right. So here, alpha is less than or equal to theta is less than or equal to beta. And H1 of theta is less than or equal to R is less than or equal to H2 of theta. So therefore, my double integral over my region of F x, y, dA is going to be the integral from alpha to beta, my integral from H1 of theta to H2 of theta of F of R cosine theta, R sine theta, R dr d theta. And so we must integrate with respect to R first. Okay, so that's what it means to be radially simple. Now, I don't know if your book uses this word, but this is the right word.
Yeah, the book doesn't use it.
Yeah. Okay, so what does that mean? Azimuthal means in the angle, that means according to the angle theta. That's all. Okay. And that looks something like this. So okay. Okay. So here's my region. Okay. This is R equal to R1 or A. And this is R equals B. Okay. And then this is theta is equal to G1 of R. And this is theta is equal to G2 of R. So basically it can change based on what the radius is. So now I see that my radius clearly goes from A to B, doesn't change. But what can change is the theta. Okay. So here now, I know that A is less than or equal to R is less than or equal to B. And I know G1 of R is less than or equal to theta is less than or equal to G2 of R. And so my double integral over my region of f of xy dA. Now I want R to go from A to B, this to go from G1 of R to G2 of R. This is f of R cosine theta, R sine theta, R d theta, dr. And these are what's the word I want? These are rare. You don't find too many problems that look like that, but you do. And just remember as a warning, not all regions are simple, are radially azimuthally. I think I spelled it wrong. Azimuth. Oh. Okay. All right, here's an exercise. So we want to change this integral. The integral from 0 to 1. The integral from minus the square root of x minus x squared to the positive square root of x minus x squared of x squared plus y squared dy dx into polar coordinates. Okay, what do I need to do?
Other region?
Okay, how do I find the region? We can start with x, okay? So from there, we know that x is between 0 and 1. And then from here, we know that minus the square root of x minus x squared is less than y, is less than or equal to the positive square root of x minus x squared. Okay, so let's work with this second part. So if I were to square that, I would get x minus x squared is y squared. So I get y squared, I'm sorry, x squared plus y squared minus x is equal to 0. So now when I complete the square, I get x minus a fourth, no, a half, plus y squared is equal to 1/4. Okay, so that lets me know that it's a circle of radius 1/2 centered at 1/2, 0. Okay, that's what I get. And so here's my region. Now, I can clearly see that that curve, if I take that curve here, I can change this to polar coordinates, and this becomes x squared is r squared cosine squared theta plus r squared sine squared theta. Why am I doing all that? X squared plus y squared is r squared. We already know that. Minus x is r cosine theta is 0. So I factor out the r. So this curve is r is equal to cosine theta. Okay. So now what I'm going to do is, if I start down here, if I start with theta being minus pi over 2, going all the way to pi over 2, I will complete the whole circle. I don't know why it won't do this. Whatever. Y'all understand what I'm trying to do. Okay. And this goes all the way around. All right, so here comes my integral. So I get the integral from 0 to 1, the integral from 0, and this curve is r is equal to cosine theta. So r starts off at 0 and goes to cosine theta. And x squared plus y squared becomes r squared. And then I still have to multiply by r dr d theta. Okay, this is an iterated integral and I can't pull it apart. So this is the integral from 0 to 1 of r cubed, the integral from 0 to cosine theta of r cubed r dr d theta. So that's the integral from 0. Okay, wait a minute. These are the wrong limits. Okay. Integral from minus pi over 2 to pi over 2. And now I'm going to get already multiplied. So now I should get 1/4 r to the 4th evaluated between 0 and cosine theta d theta. Integral minus pi over 2 to pi over 2 cosine to the 4th of theta d theta. How do I do that? How do I do it? Where are my Calc 2 people? Show me I taught you something.
We split it into.
What'd you say?
We split it into cosine squared and.
Split it into cosine squared squared. Good. So this becomes the integral from minus pi over 2 to pi over 2 of cosine squared of theta squared d theta. Well, cosine squared is 1/2 times 1 plus the cosine of 2 theta. So therefore, when I square that, I'm going to get 1/4. Didn't I have a 1/4? So now I'm going to get 1/16. Because I already had a 1/4. And then this gets squared, so that gives me a 1/4. So now I'm going to have 1/16, the integral from minus pi over 2 to pi over 2 of 1 plus cosine of 2 theta squared d theta. 1/16, the integral from minus pi over 2 to pi over 2 of 1 plus 2 cosine 2 theta plus cosine squared of 2 theta d theta. So I get 1/16, the integral of minus pi over 2 to pi over 2. So now this cosine squared of 2 theta is 1/2 plus 1/2 the cosine of 4 theta. So I'm going to take this 1/2 and this 1 and add them together and get 3/2 plus 2 cosine of 2 theta plus 1/2 the cosine of 4 theta d theta. And after you do all of that, your answer is 3/32 pi. Okay. Let me look at our schedule. Y'all, I think, why do I feel like y'all can't possibly have another test? We have 2 more weeks, right? So your projects for those who, 2 more weeks. For those who want to do projects, they're due, I think tomorrow?
Yeah, tomorrow.
Tomorrow. Okay, so yeah, you do have a test next on the 27th. So y'all have some time. Good, we have plenty of time to do some work because we are in good shape. We're actually almost a week ahead. So
How
yes,
how far are we going to the
we're going to
end chapter?
15, we're going to 15.5.
Oh, okay. Isn't that next section?
That's the next section. We're going to 15.5. So like I said, we're a little ahead. I don't know how we got so far ahead. The only thing I could think of is that when we went online, you guys haven't been asking as many questions. So just keep going.